Okay, give me a sec.
Yo, this is D-Dog David. How y'all doing?
Hey guys, as you can see, I have my assistant here with me today for the video about spectroscopy. So spectroscopy, hopefully you recognize that the first part of the word spectro comes from spectrum, and that's when we're talking about things that have to do with light. So let's talk about the interaction between atoms and light. So light is really the key to understanding our modern version of the atom. Remember, we talked about that cloud model of the atom. And so it has wave properties, and you probably learned a little bit about that, but it also has particle properties depending on the way that you measure it. And we call a packet of light a photon. So any of you Star Trek fans, photon torpedoes, that's what they are. So the first thing we need to look at is the electromagnetic spectrum. This is in your yellow packet. You should pull it out, pause if you need to, and just take a look at this so that you can see in front of you what it looks like. All types of electromagnetic radiation are light. And you can see, if you look at the visible light section, that it is really a very small part of the electromagnetic spectrum when you look at all the other types of light. There are different things that I'm sure you've heard of. Things like x-rays. You go to the dentist, you get an x-ray, or if you've ever broken or thought you've broken anything. Ultraviolet light, I'm sure that you guys know that that comes from the sun. Microwaves, infrared, that is used in things like scanners and that sort of thing when they scan price tags. Radio waves, I'm sure you're familiar with those. I'm guessing that most of you have a cell phone. I know I like mine. So radio waves are how we transmit radio and cell phone signals. When we talk about wavelength, we have to think about how we measure it. So wavelength, what unit does that imply? Hopefully you said meters. It's the distance between two equivalent points on a wave. So if you see at the top of that little picture, it's got crest to crest, that's the top of the wave, or at the bottom, trough to trough. And those are the equivalent points on a wave that we use for measuring. And wavelength has this funky little symbol. It's a Greek letter, lambda, and that is the symbol that we use for wavelength. And if you think about length as a measurement, remember that we always measure it in meters, so some type of meters. Nanometers, picometers, you're going to get into some of those prefixes where we haven't used them, or you may not have heard of them before, but we're using them now. So make sure you go back and buff up on those before the quiz. So let's talk about the characteristics of light. There's also frequency. That's not a V, that's a Greek letter nu. So V, it looks like a V when you write it. It's the number of times a particular point on a wave passes by an observer in 1 second. So if you have somebody standing at the end of the waves on the left-hand side of the screen, it's how many times each of those waves passes by that person in 1 second. So you can see that there are some differences in the wavelengths and the frequencies of the different colored waves. So think about which one has the highest frequency. Hopefully you said purple. Some people think it looks pink, that bottom line. How about the lowest frequency? That would be the red. And if you think about it, look at the wavelengths. So we said that the red had the lowest frequency. Does it have a long or a short wavelength compared to the purple one at the bottom? It has a much longer wavelength. So we want to think about that relationship between frequency and wavelength. So the frequency is measured in hertz. Hertz is also equal to 1/seconds, and that'll be important when we do calculations. So wavelength and frequency are inversely related. If wavelength increases, frequency decreases. As one goes up, the other goes down. And we have an equation for the relationship between frequency and wavelength. It's C equals lambda nu. So C equals wavelength times frequency. And C is actually the speed of light, which is a constant. That means it never changes. Light always travels at that speed, 3.00 times 10 to the 8th meters per second. And then let's talk about some characteristics of light. There are lots of frequencies and wavelengths of light, and you kind of saw that on the little chart from your reference table earlier. And you can see again, this one looks a little bit different, but that visible region of light is really small compared to all of the other parts of light. So we can only see very small sections of that light spectrum, but there are lots of other important types of electromagnetic radiation or light. One photon of light really can only transfer a certain amount of energy. And the way that we figure that out is energy E is equal to H times nu, V the little Greek letter nu. So E is the energy of that one photon. H is called Planck's constant. And again, when we say it's a constant, it never changes. And that is 6.626 times 10 to the negative 34th joules times seconds. And then nu, the little v, is our frequency. So that might be given to you in a problem, or you may have to calculate it. And energy, if you think about it, if frequency increases and we're multiplying it by a constant, then energy will increase. So those ones are directly proportional. If one goes up, the other goes up. Let's go back to this electromagnetic spectrum now and think about which light can do the most damage to you. So think about what we know about wavelength, frequency, and energy. Pause the video and think about those relationships. Okay, so if you think about it, the highest energy is going to have the highest frequency. And there's nothing on this chart about frequency, but if you look, we know the highest frequency will have the shortest wavelengths. So the shortest wavelength types of light are to the right side. The short wavelength, high frequency has the highest energy. And if you've ever heard of someone having cancer and having gamma knife radiation, that's a very strong type of radiation that's used to treat tumors, a lot of times brain tumors, and it is extremely powerful and dangerous. So you can see the sun, the ultraviolet light from the sun, has higher energy than visible light, and we know that it damages us because we protect ourselves from it with sunscreen. X-rays, you go to the dentist to have an x-ray, first thing they do is put that lead apron on you, and then the person who's taking the x-ray steps out of the room to the other side of a lead wall so that they're protected from those x-rays. All right, so let's look a little bit more at those relationships and just kind of solidify that. So wavelength and frequency are inversely related. One goes up, the other goes down. It's a mathematical relationship. Frequency and energy are directly related. So let's think about what the relationship must be between wavelength and energy. If we know that wavelength goes up and frequency goes down, energy goes down. So if wavelength goes up, energy goes down. They are inversely related. Let's look at a couple of practice problems. So in this problem, it's giving us a laser pointer emitting light at 532 nanometers. And it's asking us to tell which region of the spectrum the light is found in. So it's asking whether it's radio waves or infrared or gamma rays. And then if it's visible, if it falls in that really narrow visible range, it's asking us to give the color. So if it falls anywhere in this little narrow range there, it's going to ask us what color it is. So if you determine something's visible light, be prepared to find the color. So let's start off by looking at this chart. You'll notice here it says that the measurement is in meters, and in our problem our measurement is in nanometers. So we're going to have to go back and convert the nanometers to meters. So if you haven't looked at those prefixes lately, you might want to brush up on them before you see them on a quiz. So let's take a look at that conversion. So we're going to convert from 532 nanometers we're going to set up our conversion factor. We want nanometers on the bottom to cancel. We want meters on the top. Hopefully you remember your scientific notation. Nano starts with N, it's -9, and that always goes with the base unit, so the one without the prefix. So 1 times 10 to the -9th. And then we put the 1 with the nanometer. And when you punch that into your calculator, you should get 5.32 times 10 to the -7th meters. So now what we want to do, I'm going to go ahead and click that off so we can look at the chart. We're going to come down here and look at our information on our spectrum. So what you want to do is you want to find 10 to the negative 7th meters. That's right here. And because it's 5.32 times 10 to the negative 7th meters, we know that it's greater than 10 to the negative 7th meters. And so you want to look at the direction of your exponents. The less negative they are, the bigger the number is. So it's going to fall somewhere in this range. It says it's 532 nanometers, or 5.32 times 10 to the negative 7th. So we want to come down here and look. It does fall between 4.0 times 10 to the negative 7th and 7.0 times 10 to the negative 7th. So we need to find out where 5.32 falls. So 5.32 times 10 to the negative 7th, if you look at these little tick marks here, 5.32 falls between 5.7 and 4.9. So this would be visible light. And it would be green. And you would need to give me both of those answers to get full credit for a problem like this.